It's trying to buffer though, from time to time.
It's trying to buffer, but not going through.
Yes.
Can you see it now?
No, can we try without webcam?
Yes. No webcam.
Okay, we're going to restart the call.
Okay, let's restart the call.
Okay, 1 second. Hello, let's try.
Hello?
Yes, try. Try to share screen. Yes,
Send.
we see the slides.
You see the slides now?
Yes.
In presentation mode?
No.
Not in presentation mode?
No.
Okay. Let me try again. Can you see in presentation mode now?
Negative.
Sure what's so. How about now?
Negative.
Negative. Yesterday it worked fine, just sharing like this. Let me try to share the full screen. How about now?
Yes.
You can see the presentation?
Yes.
Presentation mode?
Yes.
Okay. All right. Thank you. And yeah, that's the problem of doing things remotely over VC. Technology doesn't.
Can you turn on the webcam now?
Okay, let me try the webcam now. Okay. How about now?
Yes, perfect. Finally.
Perfect. All right.
Beautiful.
Okay.
Yes. Let's go.
All right. Sorry for the delay, but again, I apologize for doing this remotely. But hopefully you guys still find it interesting and valuable. So I'm going to talk about HHVM, which is this PHP implementation that we've been working mostly at Facebook for a number of years now. So just a brief introduction about myself. So I have background mostly working on compilers and performance analysis and code optimizations, and I've been doing this for 15 plus years at this point. And I spent the last 5.5 years here at Facebook working on HHVM and its predecessor system, and mostly trying to push the performance of PHP as much as we can. So let me start by saying why PHP. Many people claim that PHP is not a well-designed language, and it definitely has some limitations and some sharp edges. But I think overall it's actually a pretty decent language, and that's why it's been quite successful. And it's been used by a number of companies, a number of websites, and it's especially used for server-side web development. And I think that there are two main strengths of PHP that made it very popular. And the first one is that it's very well integrated with web servers. And the second one is that it enables a very rapid development cycle. So even if you're working on a very large code base with millions of lines of code, you can just go and make some edit make some changes in your source code, save that in your editor, just Alt tab, go into your browser, reload it, and you see the change almost instantly. So that's something that's very nice, especially for working on a very large code base. That's something that once people are used to it, they don't want to, if you take that away, they really don't like it. And I think as an attachment for PHP's success, if you look at the top websites on the planet today, I pulled like this list a couple of days ago from this website that monitors things, and these are like the top 6 websites according to traffic that they drive today. And among these top 6, 4 of them actually are written to a great extent in PHP: Facebook, Baidu, Wikipedia, and Yahoo. So I think that's kind of a very good attachment for how popular the language is and how important role it plays these days. So now let me motivate why HHVM. And running some of these large websites with lots of traffic, very high load, you need very high performance hardware and software systems. Companies running these will often need to lease or build their own infrastructure, very large data centers, lots of racks of machines to be able to keep up with all the traffic that they drive. And even though PHP has about 20 years now, there was really just one full implementation that was widely used before we started working on it a few years ago. And the standard PHP implementation is not very efficient. It's actually just an interpreter. And for people familiar with different ways you can implement a language, know that the interpreter is not the most performant one. So PHP performance started to become a problem for us at Facebook back in 2007, trying to scale our data centers. And that's when we started investing on looking at alternatives. And our first approach was what was called the hip-hop compiler, which was actually a static compiler, compiling PHP into C++ and then using GCC in the backend to compile, to generate machine code. And it was actually a very interesting system, and we deployed that to production and used it for a few years inside the company. And but I'm not going to go into a lot of details on it, but the main limitation that it had is that we couldn't really use it for development. It was pretty slow, as you can imagine. If you take a large code base in PHP, there's overhead to compile that to C++ and then use GCC to compile a very massive code base. Even after lots of optimization, it was still kind of slow. It was breaking that fast development cycle that I mentioned in the beginning that PHP offers and that people really like. So this motivated us to start working on HHVM. And there were 2 main goals with HHVM. One was to try to unify the development and production environments and using dynamic compilation to be able to do a faster job and just recompile portions of the code that were changing during development. And the other one is that we thought that there was an opportunity to generate better code and to beat the performance of the static compiler using a just-in-time compiler. So I mentioned a few times we wanted to make things more efficient, to improve performance even further, but let me give you guys an idea of how much we've been able to improve performance. So this is a graph showing the historical performance improvements that we achieved running Facebook over the years, and we keep track of these internally. And there are lots of things going on here, so let me explain exactly how this was obtained. So the graph starts in January of 2010 when we deployed the hip-hop compiler to production. And at that time, it was running 2 times faster than with the PHP version that we were running the site at the time, which was 5.1. And we ran with that in production up to January of 2013, sorry. And the way we calculate the wins here is that with every new release of the compiler, we would compare the performance versus the previous one, and just accumulates the wins over time. We couldn't measure and compare directly with PHP since the summer of 2010, because once we had our own compiler, we started adding new language features and diverting a little bit from PHP in ways that we couldn't run our code base on top of PHP anymore. So the methodology here is really measuring the performance relative to the previous versions of the compiler. And so by the end of its lifetime, the hip-hop compiler was about 6 times faster than PHP using this methodology. And at that point, we released HHVM to production, and since then, we keep improving performance quite a bit as well. So I just want to emphasize that this doesn't really mean that we're 26 times faster than PHP. That's not a fair comparison. We can't run Facebook on top of PHP, as I said, but this gives an idea of the magnitude of the wins. But there are lots of things, lots of moving parts, as I said here. We keep the Facebook website changed quite a bit over the years as we're measuring these. PHP has evolved quite a bit as well. And also the hardware that was used to do the measurements was changing over the years. So many things changed, but this hopefully gives an idea of the performance improvements that we've been able to achieve. So because of that, companies running large websites also got interested in HHVM, and among those top 6 websites these days, Facebook, Baidu, and Wikipedia are all running on top of HHVM. They saw some good performance benefits from switching to HHVM, and so they did it. And there are a lot of other adopters also. Many companies out there using, including Box, Etsy, Slack, WordPress, and whenever they switch, some of them do some measurements and report some data. And as one data point here, when Wikipedia switched to HHVM, they reported a 6x performance improvement in reduction in CPU utilization in their servers. So now I'm going to switch to give an overview of the compilation pipeline inside HHVM, just to give you guys an idea of what's going on there. So we start with PHP code and go all the way to machine code, x86 code. And there are 2 separate components here. There's one component that is ahead of time compilation that we do. And we go all the way from PHP up to bytecode in that point. And this is an internal bytecode representation that we came up for PHP, and you can think of that as Java bytecode. It's the analogous to that. And to get to bytecode, we first go build an abstract syntax tree, which is it's the output of the parser, very standard for compilers, and we do some optimizations at that level. And in these components, we actually reuse parts of the hip-hop compiler, the predecessor system we had, and we do optimizations at that level, and then emit the bytecode and do more optimizations at the bytecode level, including type inference to try to infer types of variables ahead of time. And the bytecode is what we actually ship to production, deploy to our servers, to our web servers. Then the web servers start executing at runtime, reading this bytecode. And then it goes through 2 different intermediate representations in the compiler, this HHIR and VASM, before emitting machine code. And HHIR is our high-level representation where we do optimizations that know the semantics of PHP and do things that still require some semantics about the language. VASM is very low level. It's pretty much assembly, x86 assembly, but with virtual registers. The main optimization we do there is register allocation. And one important thing here is that the bytecode is still untyped. Even though we do type inference ahead of time, that's kind of opportunistic and trying to infer types as much as we can, but we don't require that. However, at the HHIR level, things are typed. We need type information in order to do a good job at that level. And I'm going to talk about how we obtain such type information next. But this is kind of an overview of the pipeline. I'm not going to go into the details of everything here. There's a lot of things going on, but hopefully this gives you guys an idea. So next I'm going to switch gears to talk about some of the challenges of improving performance, and I'm going to talk about some of those components and how we design them to be able to obtain high performance. And so the first challenge I'm going to talk about is dynamic typing in PHP, or the lack of static typing and the challenge that imposes. The second one is the huge amount of code that we need to deal with when running a large-scale website. And large amounts of code pose us two challenges, separate challenges. First one is the compiler speed. The just-in-time compiler has to be very fast to be able to compile lots of code. The second one is that the code locality becomes an issue to us because of the massive amounts of code that we generate. And the third challenge I'm going to talk about is reference counting in PHP. So we'll start with dynamic typing. The problem with dynamic typing is that if you don't know the types of the variables that you're operating on, you basically have to generate very generic code that even if you see an addition, you have to consider that the operands may be an integer, a double, or a Boolean, or an array, an object, and these things that sometimes happen in scripting language, and they need to work. They have some semantics, you need to preserve the proper behavior in those cases as well. So a basic principle we have in HHVM is that to obtain performance, we need to know the types, and we only want to operate on typed code, and we need to, so that we can specialize and generate very efficient code for the common case, for the real types that are flowing through the system at runtime. And there are two ways that we obtain types. The first one I alluded before is doing type inference ahead of time, and we used to do this at the abstract syntax tree level, based on the code we had from the previous hip-hop compiler. And later we switched to do it at the bytecode level, which gives us some more fine-grained information. And we saw some a small performance improvement by doing that as well. In addition to ahead of time, we also try to obtain the remaining type information at runtime. And there are basically two architectures to HHVM that we explored in the JIT to obtain types at runtime. The first one was what we call the Tracelet JIT. And the Tracelet is basically a small piece of code that is type specialized. And the way we obtain the types to JIT that piece of code is by inspecting the live state in the virtual machine. So if you need to compile a piece of code that is adding two local variables, you go and check the types of those local variables and generate code for those types that you're seeing. And then you execute that piece of code, and now you need to know type information about other things. Then you go and inspect the types, the live types again, and JIT that next block of code. The second approach that we've tried, and that's what we actually have been using today, is a more sophisticated approach based on profiling. So we generate profiling code, and that we are going to run with that for some time. And with that, we collect profile information about the live types of variables and expressions, and then we're able to generate or to compile a larger piece of code using all that type information at once. And compiling a larger piece of code, you can think typically a whole function or even multiple functions doing inlining and things like that. So I'm going to illustrate how these two different approaches work in practice. And here's a small example of one function in PHP that just adds goes over the first n elements of an array and adds the ones that are greater than 0, and then returns this sum at the end. So the different colors here illustrate how we would break the code in tracelets. Each of the different colors here in the loop show parts that would be compiled differently, separately as a different tracelet. So we would end up with a Tracelet JIT, we end up generating all these code blocks here, compiling them separately, and each translation starts with some type guards that I'm representing here in the red box at the top, checking the types of the variables that you need to do the computation, and then doing the actual computation specialized for those types. And here I'm just representing the code as the bytecode, but that's not important. For a piece of code that is actually polymorphic, say the sum here, the statement in this example, if the elements are sometimes double, sometimes integers, we end up generating multiple tracelets for those code blocks to handle the different types that we see at runtime. With the region JIT, what we do is basically do that same kind of translation with a Tracelet JIT in the beginning, but we also insert some profiling counters there to know how often we are taking different paths in the program. Once we do that, we can figure out what are the hot paths that we're really taking, and then recompile that as a single unit of code by just selecting the hot code and giving the whole thing to the backend of the compiler. And then it's able to do a better job because now it's compiled a larger piece of code, can find more redundancy, more dead code, and hoist things out of the loop, as in this example. Okay, so now the second challenge I want to talk about is the huge code size that we have to deal with. And for HHVM, running a large website like Facebook, we end up JITting hundreds of megabytes of code at runtime. And this is after the server has started, right? And you start taking traffic and you start compiling code and you have to keep up with the web requests that are coming in already. So you have to make sure that you handle this situation very well. And in addition to the dynamic code generated by the JIT, the HHVM binary itself has a lot of code in it. And these days it has about 130 megabytes of code. So if you put these two together, we end up with about a half a gigabyte of code being executed at runtime in the server. And this is pretty challenging, especially if you compare with the size of caches in the processors. And here are like the specs for Intel Ivy Bridge processor. And it only has 32 kilobytes of L1 iCache, for example. And even the last level cache, which is shared among all the cores, has only 25 megabytes. And also the TLB, which the TLB is the translation look-aside buffer used to do address translation from virtual to physical address. It can only, at any point in time, can only handle 16 megabytes of code. So if you compare the size of caches with the size of the binaries they have, you see that we have a great challenge to make things fit in there. So as I said, there are two aspects to the code size. The first one is the JIT speed. We have to make sure that we JIT the code and that we don't incur a lot of overhead doing that. And a very common strategy is to actually cache the code once you JIT it. So you compile the code and you save it in a code cache or a translation cache. And we do that here as well, and so that we can reuse the code across multiple requests. Another implication of JIT speed is that we end up having to building a custom JIT compiler so that we can tune it and do the proper optimizations that really buy us something and avoid things that would be too expensive and not buy as much in the end. And this also means that we cannot rely on things like LLVM, which is a very common way of building a compiler these days, is to retarget. You just target your front end of the compiler to generate LLVM intermediate representation and then rely on LLVM to do optimizations and machine code generation for you. That doesn't quite work, and actually have even invested quite a bit of effort trying to assess that and build a backend for our JITs based on LLVM. And there are two interesting findings that we had in that exercise. The first one is that LLVM is really, really slow compared to our custom JIT. It was about 200 times slower than our JIT. And despite that, we thought, okay, maybe we can still use it for the really hot code, and if it's able to give us some much better performance for the hot code and still use our custom JIT for the rest. But it turned out that even after trying to optimize it quite a bit and looking at a lot of things in LLVM, it was still not able to be the performance of our custom JIT. So we ended up just giving up on that completely. And so the custom JIT seems to be the right solution here as well. And the last thing I want to mention is that in general, for JIT speed, you have to be very careful with what optimizations you do, and only do the ones that really pay back good wins to to justify the cost of performing the optimization in the first place. Okay, so now I'm going to talk about the code locality and some of the things that we've done in HHVM to address that problem. And one of the things in the JIT is that you have to be very careful with function inlining, how much code you're willing to inline. So inlining is an optimization that usually buys compilers quite a bit, and Java claims, yeah, 20, 30% performance improvement by doing inlining. But in our case, we have to be very selective. If you start inlining too much, you grow the code too much, now you blow the caches and you actually degrade performance very easily. So we have to be very selective, but we still got some good wins by doing inlining on the order of 5-7%, I think, these days by doing inlining in HHVM. But it's not as much as other languages, basically because we cannot do it as aggressively. Another thing that we do for code locality is to use profile information to lay out the code in the code cache. And this goes very well with the region JIT design that we are currently using that I mentioned earlier. And because once we collect profile data, we know what are the hot paths. We can lay out the code to make sure that the common paths are next to each other and things hit on the cache more often. Another thing we do is to split the code and actually put it very far away in a different region of the translation cache so that it doesn't get in the way of the hot code either. Another thing we've done is we have lots of helpers that we call from the JIT code that are written in C++ and compiled with GCC, and some of them we've gone long ways as to even rewrite them completely in assembly to make sure that we get the best code, because we couldn't tweak GCC to do a good job. And other things we pulled out of libraries, because libraries sometimes have very optimized implementations, but very generic ones that are very large. And in some cases, we rewrote library functions in assembly, just a small version that turns out to be better for us because it has a smaller memory footprint. And another thing we've done is in the static code, we also invested some effort to try to improve the layout of the C++ compiled runtime. And we do that. One of the main optimization we do there is to reorder the functions in the binary to make the common paths of execution be adjacent functions in the binary. And that improves ITLB performance quite a bit. And we do this using this a small tool that's also available as open source called HFSort that we built. And this is something that's applicable more generally outside of HHVM. And we actually use that in other binaries inside Facebook as well, and got very nice wins. I think for HHVM, we got 7% performance improvement by doing that optimization. So it's pretty significant, and got even bigger wins for other binaries. So if you have larger binaries with ITLB problems, I suggest you take a look at this. And one last thing we do to try to improve code locality is to make use of some huge TLB entries that the x86 processor has. So these are 2 megabyte entries there that you can map memory on 2 megabyte pages to make use of them. And we use this for both the static code and also for the dynamic code. And this also gave us on the order of 5% performance improvement by using those. Okay, so now I'm going to switch to the third challenge I mentioned, which is reference counting. And reference counting is used in PHP for memory management, which means that associated with every object, there's also a count field that counts how many pointers you have in that object. And as you pass the object around and create more reference, you have to go and increment this count. And whenever that count goes to 0, that means, okay, there are no reference to that object anymore, so now you can free it. And if it's an object with a destructor, you have to execute the destructor at that point. And this is not the most advanced memory management scheme. There are much fancier garbage collection techniques out there. But unfortunately, the fact that PHP uses reference counting actually leaks at the language level, and it's visible to the user in a couple of different ways. And the first one is that the object destructors have to be called exactly when that count reaches 0. So they have to run precisely at that point. Another one is that with some weird things with how arrays and work and copy and write, which I'm not going to go into details as well. But as you can imagine, whenever you are accessing an object, passing things around and incrementing and decrementing this count, this incurs very large overhead. And that's one of the things that we noticed early on in our JIT. And one of the ways we address that is that in the HHIR level in the compiler, we represent these increments and decrements of the count field of objects with explicit instructions in the intermediate representation, illustrated in this figure here, with instructions 10 and 11 here. And then once we represent those in the IR level, we can also do lots of optimizations to try to analysis and optimization to try to prove that you don't need those increfs and decrefs in many cases and go and eliminate them altogether. So in this case, you can come and prove that you don't need them, that no one will observe the change in the count, and then eliminate those instructions. This is probably one of the most expensive optimizations that we have and more complicated in the JIT, but it's worth like 5% performance improvement for HHVM. So we went ahead and did it and implemented it, and it's totally worth it. But that's going back to that principle, as I mentioned, it's complex, but it's really important, so we are willing to pay that cost. Another thing that we're trying to do that I mentioned before is that there are better garbage collection techniques other than reference counting, and we are actually have an ongoing effort to try to switch over to a tracing GC. And we have something running right now is able to find garbage cycles, which reference counting is unable to. Whenever you have a cycle, the count is never 0 for any of those, so of the elements involved in the cycle, so you don't free that. So we are currently able to use a tracing mechanism to identify cycles and free them. But we couldn't get rid of the overheads of the increments and decrements yet. But we're trying that, and this is going to have implications at the language level. Have to go and change or make sure that the PHP code runs properly with a tracing GC. So this is a hard problem that we're tackling. But we believe that potentially it can give us some good performance wins, because as I showed earlier, just doing that optimization at the JIT code bought us like 5%, but there's still lots of ref counting operations happening inside the runtime in the C++ code that we're not able to optimize with our compiler, and that code is being compiled through GCC. GCC doesn't understand the semantics of reference counting, so it's not able to do the same kinds of optimizations there either. But with a tracing GC, we think we can eliminate some of these, more of these overheads. Of course, garbage collection has its own overhead, so we're going to see where we land there, but we're willing to try this. Okay, one other thing I want to mention, in addition to performance, HHVM also has support for another language, not just PHP, but this language called Hack, which is basically a dialect of PHP that we designed at Facebook. And Hack extends PHP with more type annotations for function return values and different types of type annotations. And that's a project that we did a few years ago, and mainly motivated for security reasons. We saw sometimes problems because of dynamic typing and people not testing the code properly. So having a static type checker was able to detect more of these errors. And Hack has a gradual typing system, which allows you to gradually migrate your code. Starting from PHP, you can gradually go and migrate things and add type annotations, and things, code in Hack and PHP interoperate seamlessly. So that's another thing that also is supported. It's not supported by the standard PHP, but with HHVM, you get support for that as well. Okay, so to summarize my talk, I think everybody here knows that if you have very high-load websites, you need very high performance software to run it as well. And PHP is very popular, has been used to build many large-scale websites, and it poses lots of interesting challenges to efficiently execute it. And in HHVM, we've been trying to tackle all these problems and try to make PHP code run as efficiently as possible. And I just want to mention that HHVM is open source, so you can play with it. If you have a large scale and need high performance PHP implementation, I strongly suggest you to give it a try. And if you have any problems trying to migrate, you're welcome to reach out to us and ask for help, and we're willing to help more people migrate to HHVM. So that concludes my talk, and I'll be glad to take any questions. I think we can do that over VC.
Some questions?
I can't hear anything, so I don't know if there's no questions or...
Hello, thank you for the speech. And do you have any plans to migrate to PHP 7, or what do you think about it?
No, we have no plans. At Facebook, we have no plans to migrate around back on PHP. We're invested on HHVM. We still try to make, at the language level, we still try to make HHVM as compatible with PHP as possible, and new language features that are being added to PHP, we also try to add them on HHVM so that people running on HHVM can benefit from them as well. But no, as a company, Facebook running on PHP 7, no, that's not under consideration. Yeah.
I think that's all. Thank you for your presentation.
Okay. All right. Thank you.
Hi, Guilherme. This is Igor. So thank you for your presentation.
Okay.
Sorry.
Thank you.
Bye.
Hopefully, did it work well?
Sorry, what?
Did it work well over VC?
Could you repeat, please?
I was asking if the
Skype is good. Yeah. Okay. Thank you.
The call, did it go well?
Yeah.
Was it clear for people?
Not so much. 15 or sorry, 25. About 25 people.
25 people, you said?
Yeah. 25 people hearing you.
Okay. Okay. But was it clear for people could you listen well? Was it clear what I was saying?
Yeah, we heard you very well. Yeah.
Right. Well.
The
Okay.
Skype was good. Yeah.
Okay.
Initial setup
Okay.
was quite terrible, but everything else was good. Yeah.
What was terrible? Sorry.
Initial setup. It takes about 7 minutes.
Yes.
Yeah.
Yeah.
So in
Yes,
future we should we can try it do before the presentation.
Yeah. Next time we should try a few minutes earlier to make sure things work. Yeah, because they don't always work as expected. Even though yesterday it worked fine, then today had some hiccups.
Okay. Thank you. Anyway, yeah, it was very good presentation. Yeah.
Okay. All right. Thank you.
Bye.
Bye.